Now that we've learned how to convert into the standard and factored forms, it's time to look at the vertex form. Like the factored form, the vertex form will provide us with new ways to analyze, manipulate, and simplify quadratics. Unlike the factored form, though, any quadratic can be converted into the vertex form through a relatively consistent set of steps. This versatility will make the vertex form a practical option for dealing with quadratics, even when they don't contain the nicest numbers. So let's learn how to utilize that versatility and convert into the vertex form. At the heart of the vertex form is a special type of quadratic called a perfect square. So like we did when working with the factored form, let's begin this video by observing some patterns that occur when converting perfect squares into the standard form. To start, here are many examples of perfect squares. And notice that the perfect squares on the left side contain addition, while the ones on the right side contain subtraction. Then, once we have those written out, our next step is to write each expression as the product of two identical linear factors. And after that, we do our double distribution for each example, and then combine like terms to get the standard form. At this point, we're ready to observe some patterns. The first thing to notice is that although these are special cases of the factored form, they are still examples of the factored form. So all the patterns that we observed about the factored form are still true. For example, the constant terms in our results are still just the product of the constants from the linear factors. But since the linear factors were always identical to each other, all of our final constants are square numbers. More importantly, the coefficients of the linear terms in our results are still the sum of the constants from our original linear factors. But since the linear factors were repeated, it turns out that the final linear coefficient is just double of the constant from our perfect square. For example, in x plus 3 squared, the final linear coefficient is 6, which is 3 times 2. And in x minus 7 squared, the final linear coefficient is negative 14, which is negative 7 times 2. This is the aspect of perfect squares that we'll focus on when converting into the vertex form. So let's go ahead and start that process. In order to build up our skills methodically, let's start this conversion process with examples that have integer coefficients and a leading coefficient of 1. Here's an example that fits those characteristics, so let's try to convert this into the vertex form. But where should we even start in this process? Well, recall that converting into the standard form was a direct process, regardless of which form we started with. Thus, converting from the standard form to the vertex form will be an inverse process, similar to factoring. This means that our best approach to this problem will be to make an informed guess at what the vertex form should be, convert that into the standard form, and see if it matches our original expression. So let's try that out. One thing that might stick out here is the constant term of 9. If we use this perfect square, then the resulting constant term will match our desired constant, since 3 squared is 9. However, the linear term is incorrect. So let's make a different guess and see if we can get the linear term to be correct. And to make that happen, we'll use this perfect square, since 5 times 2 will give us the 10 that we want for our linear coefficient. Unfortunately, we can quickly see that while we do get the correct linear term, we don't get the correct constant term. This shouldn't come as a surprise though, because only certain special quadratics can be represented with just a perfect square, and our original expression is not one of them. So what should we do here? Well, recall that the official vertex form isn't just a perfect square. There are a couple extra pieces to the form. First, our perfect square gets multiplied by the a value, and any value for a other than 1 will change the coefficients in our perfect square. But since our example starts with just an x squared, we can ignore a for now and shift our focus to the k value. We can think of this k value as an adjuster that allows us to fix our perfect square. And since the guesses that we made earlier weren't off by much, let's try fixing our guesses with k values. So, looking back at the guesses that we made, how would we like to adjust each guess to make it match our original expression? Well, in our first guess, notice that we got a 6x, but wanted to get 10x. This means that if we just add 4x at the end of our expression, we'll be able to combine linear terms and get the correct result. We can do the same thing for our second guess. In this case, our constant term was too big, so we need to subtract 16 from our guess to make the expressions match. At this point, though, we have two expressions that both involve a perfect square, and both match our original expression. So, which one is correct? Which one is the actual vertex form? You might be tempted to rule out this option since we used subtraction instead of the addition that's in the official vertex form. However, as we've seen before, it's really easy to rewrite subtraction as addition of a negative. It turns out that the real problem is in this expression. Notice here that the expression we added after our perfect square has a variable in it. But in the official vertex form, k is supposed to be a constant. Thus, we're only allowed to adjust our perfect square by a constant, which means that this is the correct vertex form. With that, let's look at a few more examples that just have a leading coefficient of 1. In this first example, we might be tempted to start with x plus 4 squared, since that will give us a 16. But remember that we want to pick our perfect square based on what will give us the correct linear term. This means that we need to cut the 4 in half and do x plus 2 squared. When we convert that to the standard form, we get the correct linear term, and we can also see that our constant term is 4 instead of 16. This is off by 12, so if we add 12 after our perfect square, that would change our simplification process this way and allow us to see that this matches our original expression. Thus, our final vertex form is this expression. Next, let's try an example where the linear term has a negative coefficient. Fortunately, this doesn't change much. Since the linear coefficient is negative 12, we can just cut that in half and include it in our perfect square. Then, when we convert our perfect square to the standard form, we can see that our constant term is 36 instead of 21. This means that we're off by 15, but instead of adding 15, we need to subtract 15. And once we do that, we've completed our vertex form. Our next example won't be much different. We'll choose our perfect square so that we get the correct linear term, and then we'll see that we want a negative 20 instead of a positive 9. And while we could keep figuring out our k value mentally, it will eventually be useful to have a bit of a formula to use here. Basically, all we have to do is take our desired constant, the negative 20, and subtract our current constant, the positive 9. This gets us negative 29, and once we add that to our vertex form and adjust our simplifications, we can see that negative 29 is indeed the correct k value. And for our final example on this screen, let's check out this problem. We'll start as usual by determining which perfect square to use. But when we convert that perfect square to the standard form, we can see that it already matches our original expression. Thus, we don't even need to worry about a k value here. We can just circle this perfect square and move along to our next set of problems. On our final screen, we're going to look at some expressions that aren't in the standard form. The only thing we have to do differently here is to start by converting to the standard form before we then convert to the vertex form. In this case, we get this as our standard form, which we can then identify as needing this perfect square. Once we convert our guess into standard form, we can see that we want a constant of -7, but our current guess has a constant of 1. Thus, we can take -7 minus 1 to see that our k value should be -8. And once we add that onto our guess, we can see that we have the correct vertex form. Let's follow that up with a problem that's in the factored form. This won't be much different from the last problem, but we will have some larger numbers to deal with. And once we get around to fixing the constant term, we can take 55 minus 64 to see that we need to subtract 9 after our perfect square. Next, we have this problem that looks like it might already be in the vertex form. Notice, however, that we're adding a linear term after our perfect square, which is not allowed in the vertex form. This means that we do indeed need to convert into the standard form, after which we can identify our actual perfect square. Then, we can finish things off by adding a negative constant, which shows us the true vertex form. And finally, let's consider this problem. While we could approach this in the same way as the previous few examples, it turns out that we don't actually need to go through all that work. Since this expression contains two identical linear polynomials that are being multiplied, we can simply rewrite the first part of this expression as a perfect square. And once we do that, we can see that we already have the vertex form. That concludes part 1 of this video on converting quadratic expressions into the vertex form. Hope you learned something new, and thanks for watching.